Oh, good afternoon, physics theories. Mr. Thompson here. Today what we're doing is we're looking at magnetic force on a current carrying wire. I thought I'd use my smart board and change things up a little bit. Alright, this current carrying creates a magnetic field, i.e. it exerts a magnetic force on another magnet. By Newton's third law, an external magnet should exert an equal but opposite force on current. That was also discovered by Ørsted. So the direction of Fm, that's the magnetic force. Consider a straight wire carrying current through an external magnetic field. All right, you have some external magnetic field shown right here, right? It's going to the left. And you have a current carrying wire. You can see the electron flow is kind of coming out towards the lower left of the page. And there's a magnetic force that's up. Now, if you look at your hand over here on the right-hand side, you can see exactly how to set up your hand to show this rule, okay? You set your thumb in the direction of the current through the wire. Your straight fingers point in the direction of the external magnetic field. And then your palm, that's the direction that the magnetic force pushes. That's the force. So it's called the third hand rule for force, okay? Another way to show this one is by using your fingers. So the electron flow is still the thumb, the index finger is the magnetic field, and then your middle finger would be, of course, the magnetic force. Middle finger can be a forceful or a powerful thing at times, right? All right, if electron flow, well, then use your left hand. If the flow of positive charge, then just use your right hand. All right, let's look at some questions here. So what we're doing is we're looking at the direction of the magnetic force in this case. Okay, so what we do is I like the hand rule rather than the, I don't know what I'd call the middle finger rule, but we're using the third hand rule for force. And so what I do is I use my left hand and I position it kind of like this, okay? So I've got my fingers, got my thumb pointing this way, and then of course this would be like my palm here. The palm is going to show the magnetic force which comes out of the page. The electrons are going this way, so I'm using my left hand, okay? Well, my arm's getting a little wider as it goes up. The magnetic field is downwards, and then the palm would be going up. Okay, try and position your hand like that and see that it works. Okay, so it would be, of course, out of the page. How about this one right here? I want to know the external magnetic field. The magnetic force is going to the right, and you can see that the flow of electrons should go from negative to positive. So here's my electrons moving. And so I'm going to position my hand so that I have the electrons going up. The force is to the right, and so what I do is I point my fingers into the page. Okay? Thumb pointing straight up, like I want to shake someone's hand with my left hand. Okay? In that case there, the magnetic field would have to be into the page. Okay? If you have any questions about that kind of thing, just shoot me an email, let me know. All right. The magnitude of the magnetic force. All right, we use a formula to do this. If it's a current carrying wire, we use Fm equals L perpendicular I times B. Notice that B must be perpendicular to L, in other words, the magnetic field, the external magnetic field, is perpendicular to the length of wire in the field. 1 Newton is known as a 1 meter times amp times Tesla. So a Newton can be a combination of meters, amps, and Teslas. L is the length of the wire in the magnetic field in M, meters, right? Is the current going through the wire in A, which is amperes. And B is the magnitude of the external magnetic field in Teslas, capital T. Note, magnetic force is always perpendicular to both B and I. If B is perpendicular to L, then Fm is at a maximum value. If B is parallel to L, then there's no magnetic force at all. Current is defined as the rate of flow of charge. And so I, current, is equal to Q over T, where Q is the total charge in coulombs, C, through the device in T seconds. All right, here's an example for you. The current balance. You have the mass of the wire, 55 grams. The length of wire in the field is 8.0 centimeters. If the wire is suspended in the magnetic field, and if 7.3 times 10 to the 20 electrons travel through the wire in 13 seconds, determine the external magnetic field and the direction of the electron flow through the wire. Okay, typical kind of question. I've seen ones like this on a diploma. So we have the idea of it being suspended, right? We know about something being suspended. It means the forces must be balanced, okay? And so forces that are balanced means that Fm has to be equal to Fg, which is the force due to gravity. But to start the problem, you have the whole idea of electrons traveling through the wire. You want to figure out the current. So I figure out the current first as Q over T. Now, how much charge is flowing through? Well, we have 7.3 times 10 to the 20 electrons, and that's going to be multiplied by the charge of each electron, 1.6 times 10 to the negative 19. That is all divided by the time interval, which is 13 seconds. So get out your calculator, Wayne, take a picture or whatever, or rewind the video as necessary, okay? And let's calculate this thing. Okay, I get this number right here, 8.9846 amperes. Okay, now I can set up my equation. So we're balancing forces. Fm equals Fg. Now you can put magnitudes around it if you wish, like this, your absolute value signs, or you can just realize that you're just calculating strengths, okay? So no negative 9.81 business, okay? All right, so here's what I'm going to do. I'm going to put in my formula here, which is supposed to be the L perpendicular. It's right up top of the page, the way that they put it, which is, L perpendicular I times B. And of course, they put the absolute value around B here. Okay, let's do that. Is equal to M times G. But this is really an absolute value thing as well. Okay, let's go ahead and put in my information that I have here. Sorry, it's just dropped down too far. Okay. 8 centimeters, 55 grams. Okay. So 8.0 e negative 2 times I, which is 8.9846, times B, the magnetic field strength, which is what I'm looking for, okay, is equal to M times G. So I had 55 grams times 9.81. Let's figure out what the magnetic field is, okay? All right, I get a magnetic field strength of 0.75007. Okay, so I'm going to round this one to sig digs, which would be 0.75 Teslas. Okay, I'm going to stop it right there and check for sound control here. All right, bye.